Hello everyone and welcome to our presentation for Lab 2. This will be on scalar fields. And specifically in this presentation, we are going to look at how weather information gets fit into a conceptual model, and then also ways that we can take weather information and then try and come up with some sort of pattern or analysis of those weather observations. So we're going to start out talking a little bit about models and conceptualizations. So if we use an example of Newton and how Newton came up with the concept of gravity, gravity was around for a long period of time. People didn't really call it gravity though. They saw objects fall and they knew that the earth attracted objects. But it was Newton who came up with the concept and the mathematical relationship based on a model that he believed the earth attracted objects and other objects attract each other. Likewise, in meteorology, we have concepts. We come up with concepts and then we try and fit the data, or the data tells us how our concepts or our models are looking, or how they are perceived on weather maps. Let's get into a few examples. So what we're going to do now is talk about conceptual models, and then we're going to talk about analysis of weather data. So conceptual models come around from years of study. People looking at weather maps notice patterns. The very first weather maps were created back in the late 19th century when the telegraph came around. After the telegraph, people could communicate with each other in real time, and they started sending weather information. So all of these weather observations were shared with other locations. People started comparing them and started noticing trends in the weather. So those observations led to kind of an analysis of the weather. Later on, we were able to take that information, and this has occurred also in the late 19th century. We were able to take that telegraph information of weather and plot it on charts. And we started analyzing those charts, looking for patterns and looking for trends. So we tried to come up with a way of describing how the weather worked, how weather changed as a result of these observations and this analysis. And the concept that came about in the early 20th century, right around 1918, was the Norwegian cyclone model. And this is where we had the birth of cold fronts and warm fronts, and also occluded fronts and stationary fronts that describe what was going on in the atmosphere. And those concepts that we came up with, the cyclone and the warm fronts and cold fronts, and also troughs, actually fit the analysis pretty well. Although our analysis were not perfect at that time. We didn't have enough weather observations. So what we mean by analysis is taking data, taking observations, and then putting those observations in some form. Typically what we do is we create weather maps or weather charts, and then analyzing those charts, looking at particular observations, particular data. Maybe we're just looking at pressure or temperature or wind for that matter, and trying to match our conceptual models, in other words, where warm fronts and cold fronts would be, with the data that we analyzed. So the way that we analyze weather information is by drawing isoplests. And then from those isoplests, those lines, we get a pattern. We can identify patterns. So there are two different kinds of analyses. There are subjective analysis and objective analysis. So with subjective analysis, what we do is we have a raw plot of weather information, data on a chart, and then we draw lines using our eyeballs, our head, and also our hands. In other words, we try and estimate the field, the data on the chart, we try and draw lines that represent a pattern. And this is also called hand analysis. And believe it or not, this is still done at many weather services to get a good feel or a good handle on the small scale features of the weather. Now, that's completely different than what we do mostly today, which is objective analysis. And objective analysis is analysis that's done of the weather data, in other words, drawing lines and looking for patterns that have no subjectiveness, no bias. In other words, it's done strictly by looking at the numbers and then interpolation. And this is done mostly by computers these days. So what objective analysis does is it puts a grid across a map, and then we try and estimate at each one of those points where we create this grid. And this grid has spaces, the grid spaces that are equal. It's a rectangular grid. You can think of it that way. But as you know, weather observations can happen just about anywhere. They don't necessarily happen at fixed distances over the ground. We have weather observations in Grand Forks and in Fargo and in Crookston. And the distance from Grand Forks to Crookston is about 25 miles, but from Grand Forks to Fargo is about 75. So you have very irregular observations across the Earth or in the upper atmosphere. But we'd like to fit those observations to a more standard grid that has a certain spacing in between each point. So to do that, we have to use some sort of interpolation scheme, and that's what objective analysis is trying to estimate the values of weather data at these grid points. So we use all sorts of different types of schemes that people have developed, mathematicians and also meteorologists have developed to determine how to interpolate this information. And most of you are probably familiar with the very basic one called linear interpolation, where you try and estimate, but using some sort of scheme to estimate those values at that point. But then there are also weighted analyses where it depends upon the distance, or perhaps maybe on some points are more important than other points. And then there are also more developed analysis schemes that are used today in meteorology, such as the Cressman analysis or the Barnes analysis. If you take more advanced meteorology classes, such as Atmospheric Science 405, you'll be working with Cressman and Barnes analyses. But right now, we're just trying to understand the concept of what objective analysis is. So here's an example of a weighted analysis, and it says, for example, here in this diagram, you see, or this picture, you see that you've got different observations, 3 different locations. You see, for example, the height of this pressure surface. Say this is maybe a 500 millibar chart, and you know that 500 millibars is about 5,800 meters above the ground. So you see 3 different observations, 3 different heights of the 500 millibar chart. You see 575 up top. Down in the lower left corner, you see 571, and you also see 569 to the right. Now, those are all in decameters, in other words, tens of meters. So if you want to estimate the height of the pressure surface at point A, you would probably use the point that is closest. That would have probably the biggest influence to point A, the observation that is closest to point A. So we'd give it more weight, we'd give it more importance. And then the ones that are farther have least importance, but still they would have some influence on the value that we estimate for that point, point A. And then there are ways of weighting the distance. You can use exponents, you can use quadratics or other things. And once again, we're not going to get into the mathematics. Just know that there are ways to estimate values, and it's done mathematically so that we don't really influence or don't include any bias or subjectiveness to our estimate. So computers can do these objective analyses very well. They can do it very fast. We have graphics packages that can also plot those, but the humans can add an element. Humans are actually kind of slow in estimating this, but we still can pick out little features on weather patterns. We can throw out weather data that we know is completely out to lunch. Computers can do that too, but sometimes humans have a little bit more intuition about what weather information is good and what is bad. And that's all we have for analysis. We looked at both subjective and objective analysis.